All right, welcome. Good morning. This is our first online lecture. So from now on, everything will switch to online mode until further notice. That's to say, we have to also arrange for the exercise class, which exercise class is on Thursday. So exercise class will also be online, as well as consultation slots. Okay, so I will send an email soon to give you the link, because my priority now is to make sure this session is smooth. So I haven't really gone as far as this. So consultation session will also be online. Everything will be online until further notice. Okay, maybe after Chinese New Year things will be better. It's kind of interesting because I kind of predicted this a while ago. So I had this on my lecture 1. So I say, in case we need to switch to online teaching, I ask you to do this. So this is something I will really want to reinforce. So please check your CU Link mailbox regularly. This is where I will send official information. So if you hear from your classmate that don't take it too seriously, you have to check your mailbox and see that the message is sent from me or from the teaching team. Those are the official information. And then I understand that online learning is not always the best. We are trying our best to improve it, and hopefully we will be able to continue to interact with each other. The chat box is one way, and also some feedback will always be useful for me. Okay, so I don't know where you are now. Is anyone at LG? Sorry, SCL4? Anybody there? It doesn't really matter. Maybe you are still in your on your bed. That's also okay. But I still would like you to help me to do some calculations. Okay. And then last thing, just common sense. Don't disturb people. Okay. And if you have anything unclear, anything you want to interrupt me, please raise your hand. Okay, so I should be able to see when you raise your hand. I should be able to see something very quickly. Chat, I need to monitor constantly. Okay, so it's good to see all of you on my screen, and let's start. Okay, so what did we do last week? Last week, a very quick recap. There's something else that we really need to finish today. So last week we start from the first law. We talk about the first law, and you have seen some application of that. Okay, I don't need to write it again. We gave a historical treatment of the first law. How did people come up with the first law? We ignore the heat energy first. We look at the work done, and then we concluded that the heat energy and the work done are kind of equivalent. Okay, that led us to the first law. The statement of the first law is basically the conservation of energy when heat energy is taken into account. And about the application, we immediately use it to look at a few cases. And in particular, we introduce some quantities that we can measure. Okay, so those are the heat capacities. So those are the ones that heat capacities. So those are the ones that we immediately obtain. So that's to say, you can have all the partial derivatives, all kind of manipulations you like. For example, in your assignment 1 that you just submitted, you manipulate heat capacities and you manipulate partial derivatives. But how do we know these thermodynamic equations are correct? So you need something that you can test. So heat capacity is really our experimental window. So you can think of it as our window for testing the structure of thermodynamics. So this allow us to test the structure of thermodynamic, to test the structure, mathematical structure of our thermodynamic. Okay, and when we talk about heat capacity, we also discuss a few concepts in detail. In particular, because heat capacity is defined in relation to the heat flow, which is not a function of state. So in order to have a well-defined heat capacities, you need to mention the constraint. So this is the constraint. The usual constraint for the PVT system are heat capacity at constant volume and heat capacity at constant pressure. Okay, so these are important. And then we also, through the examination of the heat capacities, we also find out some relationship between the two. Okay, so we also derive the relationship between all these heat capacities, relationship between the two. Okay, so we define them and we went through them, and then we found some relationship between the two. Or what are the relationship? The relationship include the difference between the two, the ratio between the two, and you get this adiabatic constant, adiabatic index cropping up through this kind of treatment. And the last part of the lecture last week, the second half of the lecture last week, we kind of pick out a particular system, and that is the ideal gas. Okay, so what do we want to talk about? Now we basically use the ideal gas to test some of our equations, because you know the ideal gas very well. So we talk about expansion. Right? And the expansion include the isothermal expansion, adiabatic expansion. Those are the standard ones that we always need to handle. And then we talk about, for the ideal gas, we get this result, which I'm going to prove to you today. So we got this result. U, the internal energy, really is only a function of temperature. Okay, and because of this, I also wrote something for you last week. I told you, if you look at the change of the internal energy, because this is true, this allows you to very quickly relate the change of the internal energy to the heat capacity at constant volume. Okay, so this one is a very special case. I put it on the board, on the whiteboard, the whiteboard, and I also put it in the notes. So let me warn you again, you can only write this down, this equation down so quickly simply because of this. So that's to say, if you don't have an ideal gas true, you might get this result. Okay, but that requires other constraint. But for the ideal gas, you can very quickly write this down, because U is only a function of temperature, and therefore the derivative with respect to T has to be total derivative, and therefore you can write du is CV C sub V times dt. And be careful of the logic. If one day you arrive at this result, you cannot use it to claim that you have an ideal gas. Okay, if you have an ideal gas, you get this result. But you can get this result even if you don't have an ideal gas. You might have situation that allows you to write this down. Okay, so just be very careful about this. This is very easy to get confused. Okay, and then we still need to show this. We still need to get this one. This is too fundamental. And then the next thing, through the examination of CP, we discover something. We discover a new thermodynamic potential function, and that new thermodynamic potential function is enthalpy. Okay, so this is one of the four useful thermodynamic potential functions. So this is one of four thermodynamic potential function. Now we kind of discover it through looking at this. Later, we are going to come up with a systematic way for you to get this. Once we learn more, we need the notion of entropy first before we can systematically write down all 4 thermodynamic potential functions. Just for you to have a reference. The other 3 you already saw internal energy U. So internal energy U is 1, internal energy U. And then the other 2 include the Gibbs function and Helmholtz function. So those are useful, very useful thermodynamic potential functions. When you do analytical thermodynamics, you will learn how to manipulate this. For example, Gibbs function is very useful when you talk about phase transition. Phase transition, for example, if you have water ice turning into water, melting, and there's some very important information you can extract once you know how to deal with the Gibbs function. And Helmholtz function is particularly useful for statistical physics. Okay, so if you want a link between thermodynamics and statistical physics, and this is a very important one, and we will see how to take advantage of our knowledge of Helmholtz function and what kind of information we can extract. So all this will come up soon. It won't be too long. Okay, but let's wait for a little bit. We will see them soon. Okay, so let's patch up this. So this is the remaining piece which we have to do, but we didn't have time to do. So this is kind of extra, but I will give you supplementary notes. I actually have everything written down, but sometimes I decide not to go into detail. But now this year I want to talk a little bit more about this. I think this is kind of cool, and we do have time to talk about this. Okay, so I already set up the problem for you. So this is the free expansion experiment. So this experiment is actually free Joule's free expansion experiment. It's important, very important, and we are going to see at least twice in this course. So this is the first time. So what do we want to cover here? So this is the experimental situation is this. You have a container that you can have a partition in somewhere inside the container. So this container is enclosed in an adiabatic wall. That's to say, you are not able to inject heat into the container, and you only have this partition that you can remove. It doesn't really need to be a very fast removal of the partition. You can also imagine having a leak here. So for example, you have a leak, and the gas particle will slowly leak into the vacuum. So this side is vacuum. This is vacuum. And this side is originally filled with gas. Okay, so this is the experimental setup. And what you have to do is you are asked to try to detect the change of the temperature when you have expansion after you remove the partition. Okay, so this is really one kind of expansion, right? Because you really let the gas change the volume. All right, so this is an expansion, and you need to measure. So what do you need to do? You need to measure. You need to experimentally measure T1 minus T0. Okay, after the partition is removed, you try your best to do this, and so after V becomes V1. Okay, so this is an expansion, and this is an experiment that allows you to conclude the internal energy is only a function of T. Okay, so remember the idea behind this. So this is the setup. At the moment, I do not assume an ideal gas. Okay, I just put some gas particle. And the point is, for the ideal gas, I will get some result which allows me to conclude this. Okay, is it clear? Did I explain it well? You still with me? Okay. Right. So what is the partial derivative that is relevant here? I think we already got to this point. So last time I say the partial derivative of interest is this. I want this experiment basically probe this partial derivative. And I also ask you what is the constraint. Some of you already answered. This is a constraint. The constraint is constant u. Why is it constant u? You have constant u because you have, so this constant u is because you have adiabatic wall. Okay, so dq is 0. You cannot inject heat into the thermodynamic system. Okay, and you cannot do work. Work is 0. d bar w is 0 because there's no pressure. Although you have volume change, right? It is there's a volume change, but there's no piston. There's nothing for you to apply force. There's no way to perform work on this thermodynamic system. So the sum of these two is 0. The sum of these two is du. So du is 0. U has to be a constant, and that's why you have this. And this partial derivative has a name. This is called the Joule coefficient. So this is called Joule's coefficient. Coefficient. Okay, it takes a symbol eta. Okay, now you look at this. You look at this partial derivative, and you ask yourself, what else can I do? The next thing I would do is I look at this. There are 3 variables. So let me try to play with a function of 2 variables. I had 3 quantities here. So I would like a relationship to relate these 3 quantities. So I can have a postulate. I would just say I will assume u is a function of 2 variables. Okay, nobody can stop me from doing this. Now I want to explore the relation between among these 3. Okay, and this comes from experimental consideration. And now I want to do some simple theory. So I want to assume this is the case, and then just write things down and see what happens. So I will show you. All right, so I can have the relationship that you know very well. So I can write something like this. Partial u, partial t at constant volume, and then t, v, and u, and this is this, and then the last one will be v, u, and this will be constant t, and this product has to be -1. Okay, reciprocity theorem. Okay, the Joule coefficient is what I'm interested, so I'm going to rearrange this product to give me this as the subject. And I just move everything, the other 2 to the other side, and I will have, let me quickly, so if I move everything to the other side, I will have at the bottom this, and this I move to the other side, and I use the reciprocal theorem, so I will have partial u, partial v, t. Okay, so I hope I didn't make a mistake. Let me check. So this one here, okay. Now here, just a simple manipulation. Again, let me stress this. I have an experimental consideration. I write this down based on thermodynamics. I did not say anything about ideal gas. Okay, so let me manipulate this a little bit more, and you will see what is this? This one you cannot do much, but what about this? The partial derivative of internal energy with respect to temperature at constant V. This is something you should recognize. Okay, this is when you see this, you will like, wow, happy. I know this because this is simply heat capacity at constant volume, right? If you don't remember, go back to last week, you see because for the PV system, when volume is a constant, I can very quickly write this as the heat capacity. This is just related. The PV term is gone. The PDV term is gone. So this is simply related to the heat flow. And this I cannot do much. So I would just write this. Okay. So just now, by the way, I want to tell you, I will give you all the notes. Yeah. Okay, here. So this one you can keep. All right. What is this 0 divided by CV? There's a message. This is interesting. What is the meaning of 0 divided by CV? Can you, this student, please elaborate a little bit? Hello? Now, I don't understand why you. Yeah. Okay. As I say, now it's good point. I hope everybody see this. Everybody see this. Okay. Now the message is only sent to me. The explanation only came to me. Okay. How should I explain it a little bit more? Here, just assume you don't know anything about this gas. Okay. So from here, otherwise I can. This is you should not assume an ideal gas to begin with. Okay, just I use some gas. Okay, so that's the point. So this is right now you cannot say too much. Okay, I give you some substance for you to measure, and then I ask you to develop the thermodynamics for me. So this is what you are doing right now. At this point, I do not say anything about the ideal gas. Now, maybe this misled the student. So this is what we want to show. Okay. Now, okay. Let me continue. If you are still confused, you can let me know. Okay. All right. Now I don't know. I don't remember what I want to say. All right. Okay. Never mind. Let me see. So I boxed this. I basically want to tell you this change to this. Okay, and then I also will give you the PDF of all these notes. So just focus on my presentation. Just follow me. Okay, don't need to write a lot of details. Okay, so here I will get this. Okay, this is just rearrangement. Okay, rearrange this equation. Let me box this. This is no. This is the result I want. Okay. we just need to focus on this. Okay, listen carefully. Heat capacity. Heat capacity is not necessary. Is heat capacity of the substance. You better believe this is something we can measure. Okay. No. Okay. I'm sorry. I get a few messages. You are going too fast. Now, just let me present mine, and then you will know. You will know the. You get the logic. Okay. Now I get one message saying that U is a function of T. And this experiment is to show that this result is for arbitrary gas. Okay, so I'm sorry, maybe I confuse you again. Just for the moment, just ignore this line. Okay, this first line is to is for me to motivate this slide. This is my goal. Just think of it as my goal. Okay, so in order to reach this goal, I designed the experiment like this, and then I develop the thermodynamic like this, and you can see this is really the outcome, not our starting point, because if this is a starting point, this is wrong, right? I write U as a function of T and V. Here I write U as a function of T only. Okay, so this is what I want to show, is my destination. So for the time being, just ignore this. Just let's start from here, and I'm going to reach this point. Okay. All right. So if I get this kind of question again, I might ignore for the time being. So I want to proceed. Okay. So this is something you can measure, and this is something you are asked to measure. This is the Joule coefficient, right? The change of temperature and the change of as you go through the free expansion, right? This partial derivative has this very strict meaning. Okay, so now we start to put in an ideal gas. Now we put in an ideal gas in the chamber. And it is an experimental fact, experimentally, even if you design the experiment really well, you cannot detect any temperature change. Okay, so if you have an ideal gas, you get this result. Okay, so there's to say, what you get is this derivative is zero. Is zero for an ideal gas. So this is zero, right? This is zero. Heat capacity is finite. This is zero. And therefore, if this is zero, what does it mean? When you change the volume, U cannot change. So U is a constant in V. So U cannot depend on V. So U can only depend on T. All right? So let me say this again. For an ideal gas, experimentally, you obtain this to be zero. Heat capacity is finite, so you have finite times zero. So this whole thing is zero. So this is zero. So U cannot depend on V, and U can only be a function of T for an ideal gas. So this is the result we want. Okay, now for the students who send me messages, are you happy? Now, it's your responsibility to tell me whether you are happy or not now. Okay. All right. And what about the rest of the class? Okay. All right. Excellent. Okay, so this is doing experiment. Now, can we do more actually? Now, if I tell you the equation of state for the ideal gas, can you get me something else? Or can you arrive at this result? Okay, the answer is yes, you can. And timing is perfect because now Now, theoretically, let's do some very simple theory. This is experiment combined with some simple. Okay. So this question, is it mainly depends on experimental result? Yes, up to this point, yes. But you also need to have some thermodynamics understanding. That why? Because that allows you to write this. Okay, it's not just partial derivatives, right? Because all these are thermodynamic variables. Okay. Now to answer this, to push a little bit more, this student Wu. Now let's have a look to see how we can do it differently. Okay, this now is purely based on the equation of state of the ideal gas. That is to say, I know if I have an ideal gas, ideal gas, what do we know? We know PV is nRT. Okay. All right. So you can show. So you can show something. This thing. This coefficient. Is T right? This is general for any PV system. Why? Why is this general? And how do you show? And who showed that? It was you. You handed in your assignment 1 today. So you in your assignment 1, you have this, right? You have this, you have shown. There are many ways to show. In the assignment 1, you are asked to, you are kind of given the integrating factor. Okay, so that's one way. Suppose you have showed this result. I will let you do it yourself. You have done it. You plug in here, you just change P is nRT divided by V and plug it into this partial derivative, right? So you differentiate with respect to T, keeping V constant, you get nR divided by V. And you multiply by this T, so you get P for the first term. And the second term is P, so you get 0. This is the same result. Okay, so for an ideal gas, you get the same result. So U cannot be a function of V. So U can only be a function of T. Okay, so this is same result. Again, I don't want to get into argument. So this is using the equation of state of an ideal gas. All right, actually, I kind of enjoyed this. I get a lot more feedback compared with last week, which is a bit strange. But this is the full treatment. Okay, so for an ideal gas, we get this result. All right. Okay, it takes a bit longer than I thought, but again, I encourage all this exchange. But some of you move too fast. And let's see the other example. Okay, I want to talk about another one because this is also related and this is kind of cool. Okay, now let me present the experiment. The experiment is this. Now imagine you have your thermodynamic system, which you can manipulate through a plug. So this is some kind of flow impedance. So just imagine you have you take a plug and you punch a few holes. So this is a flow impedance, right? So it's a bit like resistance, but then you use it for to look at fluid. Okay, so I have some gas here, which I want to push through to the other side. Okay, so this is another kind of expansion. When you go to the other side, you have volume change, and you will also have pressure change. And you are asked to do the same. Now, experimentally, okay, again, this time I will be careful. I won't tell you the result. Don't tell you the destination. I will tell you what we want to do. So we want to measure want to measure T2 minus T1. Okay, so what happens here through the plug is very complicated. You might have turbulence. It's very hard to analyze thermodynamically. But you can analyze the equilibrium situation before and after. Okay, so you can imagine having a body of fluid. Just before you push, at some instant, just before you push the piston, you can have well-defined P1, V1, T1, and then you push it through, and things can get very complicated. And once you reach equilibrium, you can look at P2, V2, T2. Okay, and the standard trick in thermodynamics is this: when you want to simulate the pressure, you always add a piston. So you add the piston for you to imagine what happens here. So this can also, now you can also imagine a continuous flow. Okay, so this is just for us to try to imagine how to look at P1 and P2. Okay, and again, there's no heat flow. So there's no heat flow, no heat flow. You have to imagine the whole thing is thermally isolated, including the piston. Okay, so no heat flow. Okay, so d bar q is 0 throughout the whole process. And now, what do we want to control in this experiment? What is the relevant partial derivative? Any idea? Now is the time for you to send me a private message. What is the partial derivative that we want to measure? Partial derivative, I don't want you to find a symbol for the partial derivative. Just use d. Okay, just tell me what do you measure in this experiment, and what is the constraint? What is the constant, the variable that you keep constant? All right, I'm waiting for your message. Now, at least the denominator should be okay, because there's okay, more. And what is the constraint? All right, so more, just one more, I will tell you the answer. Okay, now this one is actually measuring the change of temperature. As you change the pressure, pressure will change here. Now this is how should I explain this? Now you will see this kind of setup, for example, in your fridge, the fridge at home, or you can see sometimes people use this as a device to reduce pressure. So when you go to this side, pressure will drop. So if you have very high pressure flow, you want to reduce the pressure, this is one way to do it. And it's not too difficult to imagine either. Sometimes I don't know whether you go hiking, you will see if you have some flow impedance, after the impedance, the pressure will be different. Okay, so another way to look at this is to imagine you have a pump here. So you can connect this outlet to a pump, and how do you constantly repeat the cycle? You can have a pump here, and then you have a compressor on the other side. and that will simulate this behavior. Okay, so you have a tube, you pump the gas, and then you connect the tube to a pump and a compressor, and that will allows you to look at this behavior. And then now that's the thing we want to establish. What is this quantity here? Okay, and nobody got it right about this. Some people got this right. Okay, all right. So let's look at the total work done on the system. So the total work done. Total work done. On the system. Okay.
Excuse me, sir.
Yes.
May I ask whether it is true that we first fix the right hand side piston, then we released it to expand rightwards?
Say again.
I mean, whether we fixed the right hand side piston initially, so later we release the right hand piston so it can expand.
Okay, just imagine the situation like this. Okay, now you push on this side. All right, and this will expand, right? So you just put your finger here and you let it go naturally. Okay, and that will allow you to feel that there's a push, right?
So the gas will not.
You don't intentionally put force on here. So this is just a device for you to read the pressure.
Okay.
All right. Okay. Let me continue first. Okay, and you will see. So on the left hand side, now once I push, what is the work done? The work done W1. Right. So this I have to break it into two segments. So the work done is P1 dV. Okay, and this work done is very simple. I basically change from V1 to 0. Okay, so this one I change like this. So the work done on the system, on the gas. Suppose this is always how we imagine the pressure, right? We can imagine there's a way to push. Okay, so there's V1 P1. V1 P1, yes. And on the right hand side, I will have the same equation. Okay, but now I will have minus P2. I will use P2. Actually, I will just use P. I don't know why this P dV. And now what do I do? Sorry, this is right. What I do is originally there's no volume, and then at the end I get this P2, and assuming this is a very small volume. Okay, I draw it big for you to see. So you might say, this process we don't always keep this P2. Okay, just imagine this is I just want to look at a small body of small element of liquid going through this plug. And for P2, I have expansion. So I'm doing work on the surrounding, right? So imagine now I have, I put my finger here, I will feel a push. Okay, so if I put a force meter there, I will be able to read the force. Then I will be able to calculate the pressure. So this is minus P2 V2. Okay, so this minus sign tells you I perform work on the surrounding, right? So this minus sign is consistent with the way I define work done. Okay, so the total work done has to be W2 plus W1, and there will be P1 V1 minus P2 V2. Okay, and I also have a change of internal energy. I don't have heat flow because everything is adiabatically shielded. So I can ask, what is the total change in U? Okay. And the total change of U will be the U after going through the plug minus the U original. Okay, and this total change of U, why are they important? Because they balance the total change in U, balance the total work done. Okay, so I can equate them. Basically, this has to balance the total work done. So I will have P1 V1 minus P2 V2. Okay, so if you are observant, okay, I will write one more line for you. So if I move everything with 1 to one side, I will have U1 plus P1 V1. This is the same as U2 plus P2 V2. Okay. All right. And what is this? This is a definition of enthalpy. H1 is the same as H2. Okay. And what is this? Therefore, what we really for the flow process, the constant is H here. Okay. So this is H. This is the enthalpy. Okay, so I think this is a cool experiment because it's related to the free expansion, but you design the experiment differently. You have a plug, and the plug reduces the pressure. And this is the flow process that you can handle, you can think about. And just an aside, I will give you the full note. I won't do it here. If you look at this, as I say, if you're observant, you might actually smell something here. Now, this internal energy U, suppose you know a little bit more about your system, that you know how to write it, write the internal energy U. For example, this internal energy U can be contributed by the kinetic energy, can be contributed by the potential energy of your fluid. Usually we talk about energy density, right? You divide by volume, right? If you divide by volume, you get some kind of energy density. Okay, so if you decouple this into the kinetic energy density and potential energy density plus pressure, this gives you the Bernoulli equation. So the Bernoulli equation can be is actually related to this. Okay, so this is for your own interest because you learned the Bernoulli equation before. You have a tube of something which is flowing. Now, you talk about pressure difference. Here we use this to simulate a pressure difference, but we don't really discuss the role of this plug because, as I say, it's very complicated. We just look at the equilibrium case. Okay, just before you push it, you look at the equilibrium state, and then after everything settled, you look at the equilibrium state. So this requires quite a few lines for you to reach Bernoulli equation, but you will see the note. I will give you something from the textbook, and you can have a look. So this is related to the Bernoulli equation. Okay, so for my purpose, I want to show this. Okay, I want to work on this. This treatment tells you I can look at this partial derivative. Okay, is it okay, guys? Now, I want to design an experiment. This is the experiment I designed, and this is what I want to measure. And what do I control now? Rather than controlling the partition in the free expansion before, how do I control the partition? I imagine I can open this wall. For example, I might have a valve that I can control externally, right? I can have a valve that I can control. I just turn this valve, then I can open up this partition. Okay, so this is how I control, and what I really control in this sense is controlling the volume. And what I really want to control if I connect to palm, connect to the compressor, what I can try to control is the pressure difference. And I want to measure the temperature gradient, which is T2 minus T1, with the constraint of a constant enthalpy. And why do I get this constant enthalpy? And these few lines here justify the constant H condition. Okay, and then this is an aside just to tell you that you can get Bernoulli equation from here. Okay, and the rest is really really identical mathematics. You have function of 3 variables. So now you assume this. Okay, I want okay, as I say, I will give you all the notes, so don't worry. I want to start from here. Don't worry, you might panic because I erase, but no, I copy. Okay. So now, same thing. I assume from this line, I assume H is a function of P and T. And then I play with the same partial derivative. I don't want to do it again, but I will let you practice. In the end, this is what I want. Right? Using the reciprocity theorem and a few lines of manipulation, I will get this line. Completely same structure as before. Okay? Completely the same structure as before. Rather than talking about H, U, I talk about H now. Okay, and what do you go to measure? And you measure this. Right? This is experimentally, you design the experiment to measure this, and this is called the Joule-Thomson coefficient. And the symbol is mu. Okay, so you go and measure your mu, and you find that for an ideal gas, mu is 0. Okay, now hopefully you get the complete logic. And now you realize if you use for an ideal gas, mu is 0. Mu is 0. Okay. And therefore, what is the equivalent statement once you decide to describe your world in terms of enthalpy rather than internal energy? You will find H is only a function of temperature. Okay. Now, the reason I like this treatment is this. I want you to understand that enthalpy is not something we just dream up and then has no practical usage. And the other thing, now this is one usage you can see. And the other thing is for you to understand the parallel between internal energy. So the parallel between the internal energy and enthalpy. Okay, so what are the parallels? So if you kind of, I don't want to push it too much. When you talk about internal energy, you talk about volume changes, constant volume, etc. Okay, so there's something that you put emphasis on. That is the volume. You look at the volume very closely. The volume of the free expansion. When the volume is a constant, you get constant heat. There's a nice expression linking the internal energy to the constant volume heat capacity. Okay, and now if you choose your world such that you think pressure is something which is easier to control, and your experiments are you are an experimentalist who is much better at controlling the pressure, then you find that enthalpy is a more natural description. Okay, that's why if you compare the two expressions, you change volume to pressure, you change volume to pressure, change volume to pressure, and vice versa, you just get the corresponding expression for enthalpy. Okay, so I think this is kind of cool. All right, so again, there's a way to show this kind of treatment. Okay, You just need to develop an equation, a similar equation, linking H and P at constant temperature. Okay, and then you can play the identical trick, put in the equation or state of an ideal gas, and you can get this result. Okay. All right, I want to say one more thing. We use this. I say one more thing, and then we have a break. I use this to play with the thermodynamic potential function H, and then my aim is to show this, right? But you can also think of a way to use this. There's some kind of fridge called Joule-Thomson cooler. That is to say, I can try to build a fridge utilizing the Joule-Thomson effect, provided that I don't use ideal gas as my working substance. All right, do you get this point? So if I don't use an ideal gas as my working substance, this partial derivative will not be zero. So I will be able to control my pressure in order to obtain cooling. So that depends on the sign of mu, and I will have to choose an appropriate substance that allow me to achieve cooling. That's to say, I want to be able to build a fridge using this kind of setup. Okay, so this is Joule-Thomson effect is something that is being used to for cooling technology. Okay, so the catch is you must not use an ideal gas, otherwise this is a bit silly. All right, so let's take a break. Online learning is tiring, and online teaching is also quite tiring. So let's take a break and come back at 12:40. Okay. All right. All right. So welcome back. I added a few annotations here and here. Okay. So and as well as here. And all this should help you to get the logic of the entire treatment correctly. Okay. So there's a question we did. There's a question coming to me about the enthalpy in the second case, but I don't understand the question. Now, most likely, the question is not very well posed. Student, you know who you are, and you can pose it better. But just at the face value, I think your statement is wrong. Okay, so this mu, think about this mu as the analog of the eta in the free expansion. And mu is only zero when you have an ideal gas. And mu is non-zero when you have a real gas. And that's why for a real gas, you can use it for cooling. Okay, so just think about it. Again, this is drawn here. Okay, and the second thing is there's a question during the break asking me whether I can provide all the videos. Now first, do you want the videos? I have the recording. Okay, so now I think I will need to check with the department whether we can provide the video. I keep the recording anyway, just in case. Okay, so I think there was some discussion last year saying that we should not provide video immediately, because then student will not come to the class and they will watch video at the very end, like watching drama, and that will be a problem. Now I will check with the department. I don't mind either way, as long as I get some of you or most of you here Now, this is important, right? You can see from today's lecture. This lecture was quite fun for me because we make these lectures together. Otherwise, I may as well just ask you to go to some YouTube and you just watch from there. I think my role here is to try to extract your feedback and then react immediately. So if you don't come to the lecture, that is a problem for me. Okay, so I hope this answered the question sent by the student. Okay, again, you know who you are. All right, so let's move on to the second law. So that is very, very fun stuff. Okay, so why do we need the second law? So first law, what do we learn from the first law? The first law, basically, you might say the first law is already very complete. It tells you everything. So first law deals with conservation, right? Conservation of energy. So if you violate the first law, there's a big problem. The process which violates the first law will not happen. Okay, but sometimes you don't really violate the first law, but the process still doesn't happen. Okay, so then you might ask, is there a way for us to find out whether a given event, a process is going to happen spontaneously? Okay, so first law tells you the energetic part of the process. And the second law tells you whether this process, even though it's energetically allowed, whether it can happen. Okay, so the classic example is this. This is an example, again, a good timing. This is an example you have seen before today. Okay, so you have the gas. And you have this free expansion. And free expansion, if you remove the partition, you have free expansion. But we never see free compression. Okay, that is to say, the reverse of free compression does not occur, although there's no energetically there's no if you have free compression, it does not violate the first law. Energetically, this is permitted, right? But it just simply doesn't happen. Okay, so there's something you also see in some book. This is what people call the error of time. Suppose you are very poor, you don't have a clock. You just build yourself a device like this. Okay, and how do you tell the past from the future? The future is the one where all the gas particles occupy the bigger volume. Okay, this is the way you tell this is the future. And the past is the instance where you have all the gas particle confined in the same in the left hand side of this diagram. Okay, so this event allows you a simple way to tell past from the future. So this defines the error of time, and this is what the second law explicitly tells you, that a certain event can happen. Okay, it tells you the direction an event can happen. Okay, now you might argue with me. So in the past, we always get this question. If you cannot have this scenario, how do you even prepare your experiment? Okay, this is a question that people always ask. Okay, if you claim that this is not possible, you cannot have all the particle coming to one side of the box, how do you even prepare the experiment? Okay, so now let me write down this in a precise way. Okay, so this is a free expansion. So my claim is this: the reverse of free expansion does not, or cannot even, does not occur. Now the keyword is here. The keyword is spontaneously. And I can, of course, prepare the experiment if I do work, right? So if I put a pump, I pump everything here, I close the valve first, and then I pump everything. to one side, and then after I get a good enough vacuum, I close the valve and I stop the pump. I can prepare this experiment. I can even think about doing this downstairs in my lab. Okay, but that is not spontaneous. That is something that I interrupt, I interfere heavily. I go down, connect my thermodynamic system to a pump. Okay, so the reverse of the free expansion does not occur spontaneously. So that is a key word. Okay, and because of the need to describe this, we need the second law. This is why we developed this. Another example is again a very famous example is the heat flow. So we can have heat flow. This is the second example. I don't know how to draw. I would just write heat flow. Heat flow. Okay, again spontaneously. Spontaneously. Okay, so you do not observe spontaneous heat flow from cold to whole body. Okay, so heat flow, so the spontaneous process is always from hot to cold. Okay, the reverse again does not violate the first law, right? There's no reason why I cannot take this amount of heat energy from cold body to hot body. Fine, but it just doesn't occur spontaneously. Okay, so now I want you to imagine something, and this is why we need the second law. And very common when we talk about second law, you see all this engine. This is related to the fact that a lot of times people want to see whether a particular process, thermodynamic process, can be done to extract a lot of work, right? So you have du is d bar q plus d bar w. So the history of thermodynamics is such that I want to be able to try to extract work from my surrounding. For example, if I can try to extract heat from the surrounding, can I use this machine to convert everything to work? And that will allows me to perform useful tasks. And this is the meaning of the heat engine, right? Something to do with the heat, and then I use it. I try to convert as much as possible to work. Okay, now I want you to imagine this scenario. Everybody can imagine, okay? So this is not too crazy idea. So I'm going to draw a heat reservoir. Okay, so heat reservoir at some temperature T. So this heat reservoir, by definition, heat reservoir is an object with infinite heat capacity. Okay, that is to say, it's a very this is a definition, but the simple words is this. If I have a heat reservoir, the temperature is constant. So this is, of course, an idealized system. If I need to change the temperature, I have to supply a lot of heat because of this infinite heat capacity. Then this is not possible, and that's why I cannot change the temperature of the reservoir. Okay, so I take a heat reservoir and imagine this simple scenario. I have a machine here. Okay, I draw a machine. This is a machine, and I'm going to take some work energy from the surrounding. That is to say, I perform work on my thermodynamic system. Now, this is my thermodynamic system, and then I want to dump heat to this reservoir. Okay, you see this setup. Now this is not too crazy, as I say, because you see every day. Imagine this is some kind of a heater. Let's say a hairdryer. Let's say you pick a hairdryer, you plug it to the wall, to the power socket, and that allows you to supply work. Okay, and then you have Your hair dryer is giving you heat and you use it to warm your body. So this is a heat reservoir. Okay, so from everyday experience, you know this is not probable. Okay, so this is definitely permitted by the first law. Okay, I take all the electrical energy and then I convert it to the heat energy. Fine, no problem. And this is also, as I say, if you use this hairdryer analog, you see it in daily life. Okay, and now I'm going to respect the first law. So I'm going to take the same reservoir. Okay, and now I'm going to reverse the process. If I reverse the process, I do not violate the energy conservation, right? So I use the same symbol even, so I have this W and this Q. Okay, so this basically say W is Q and this one say W is Q. I don't really care whether the arrow is pointing up or down. All right, so I take a machine which I will name later. There's some machine which will do this. I will extract heat from the reservoir and then convert to work. All right, so let's see what happens. This is permitted by the first law because, as I say, I just have Q equals W. No violation of the conservation law. So this is also permitted by first law. But unfortunately, this is not allowed. This is you do not see this process in nature. So this is forbidden. But it has to be forbidden by something else. That something else turns out to be the second law. Okay. And in fact, when we learn second law, you will see a lot of different statements of the second law. Many of them uses this engine, and this is through this engine, study of this engine, we discover that we need something else to describe whether a process is possible or not. Okay, and this, in fact, is one famous statement. This is called the Kelvin statement. Kelvin statement of the second law. Of the second law. You have many equivalent statements, and this is one of them. And that's why, for the reason that will become clear later, I'm going to label this as tilde K. Basically, tilde K, the reason I do it this way is because this particular engine is not possible. So that's why I don't want K. It's a negation. So this is tilde K. Okay, and what is possible? What is possible is this. If I modify this a little bit, it will become possible. So I will copy this. I think it messed up the page. Sorry. Okay, so what is possible is this. Okay, fine. If I modify this in such a way, if I add this to make this possible, I need more. So I cannot do this. This is not allowed. But if I allow some heat to go to another reservoir, this is possible. Okay, and this heat engine with the yellow portion included is permitted. Okay, so I color code for you. Okay, so heat engine with yellow part included is permitted. Okay, and in fact, this is a typical scenario we want to study. And this thing here is called a thermal waste. Okay, so a typical engine requires two reservoirs. You cannot just simply extract all the energy from one reservoir and convert to work. And if you look at this, what does it mean? It means you cannot have an engine which convert heat to work with 100% efficiency. You must have some loss. And the loss is simply because you need to dump some heat to the second reservoir. Okay, so if you have an engine which is 100% efficiency, this is simply not available to you. Okay, so let's look at this heat engine. We talk about heat engine, and we see this in Blundell, page 132, with a different picture. But anyway, I just want to give you some story. A heat engine, it might be very abstract to you, but this is one of the simplest heat engine that I can tell you. I can spend some time to explain to you. Okay, so where is the heat component? This is the heat component. So you have some fire and you have some water here. Okay, so you have some water, and then you heat this water, this body of water. So this is the heat source. Okay, so what is the aim of this device? This is called the Newcomen engine, and this is a heat engine. So you convert heat to work. And what you want to do is you want to be able to maybe use this to lift some heavy mass. For example, you can use it to lift a bucket of water from the well. I don't know how to draw it now. Water from the well. Okay, so this is under the ground. You want to lift this up. Okay, so this thing can turn like this. The pivot is here. You can turn like this. Okay, how do you initialize this? You can think of it this way. This is connected to a piston. Okay, and there's a valve here, there's a valve here. So initially, let me close all the valves. This valve is closed, this valve is closed, and this one is closed. And when I heat this the water in the reservoir, I will get a lot of vapor. So if I open the valve, if I open this valve, the vapor will go up and it will push the piston up. And then the counterweight on this side, this is a counterweight, will go down, right? So I will push the piston and counterweight will go down. And then when it's go down far enough, I hook up my, my bucket of water. Okay, so this allows me to initialize it. And how do I then lift the item? I go to look at my engine again, and I see that there's this blue color part is water, right? This is water, and it's cold water, and this pink color part is hot vapor. So if I let the water into this chamber, equipped with the piston, so this is my piston cylinder device, if you recognize it. Okay, so the cold water will go in, and then the hot vapor will meet the cold water and it will condense. And once it condenses, it will drip back to the chamber at the bottom. And of course, at that moment, I already stopped heating the water source, the water. And then in this case, all the vapor will go, pressure will drop, and the atmospheric pressure will push this piston down, and then I can lift my bucket. Okay, so this is a heat engine, right? It's not as crazy idea as you think. And today everything is on computer, so you might not appreciate this. You might say, I send a command and then the bucket of water will come out automatically. But in the past, you don't have this kind of luxury. You have to think how to extract work using thermodynamics. Okay. I kind of like this picture. This is, I think it's very cool. Okay. So now to convince you that heat engine can be very real, can be as real as that, let's look at some simple idea. So this is a typical drawing for the heat engine. And for now, let me say that I'm going to use a symbol theta. rather than T, because I want to reserve the symbol T for the thermodynamic temperature. Now, if you have seen this kind of material before, you know they are the same. But because I want to be able to prove that they are the same, I cannot use the same symbol. Okay, so I will reserve the symbol T for the temperature you measure in Kelvin. And right now, let's just look at this theta as some temperature, which is theta 1, which describes some temperature which is higher than the temperature theta 2. Okay, so let me copy the picture I have earlier. I told you this engine is not allowed. If I stop here, it's not allowed. Okay, so if I take all the heat from theta 1, this is the reservoir at high temperature. It's color coded for you. Red means hot. If I take all the heat from Q1 and convert everything to work, that is not allowed. Okay, now it's not difficult for you to imagine this engine is also not very efficient. You have a lot of loss everywhere. Okay, and then this is a bit more complicated than this idealized engine, but you know you need to always heat. You need to it's not a very efficient piece of equipment, although it's very romantic to see this in a modern textbook. Okay, so here this good luck, this is not allowed. You need to have some loss. Okay, theta 2. Yeah, now this is an engine which is good for us because we already know how to handle this. Okay, and why do I say so? Because last week we learned about Carnot. Okay, I want this picture here. Last week we spent time to look at isothermal expansion and adiabatic expansion. So this is a picture which you can find in your notes. Okay, solid line is adiabatic and dashed line is isotherm. So if I go from A to B, so this is a cycle. I go from A to B to C to D and then to A. And this is plotted in a very realistic way. I actually put in some equation to draw this figure, so it looks a bit distorted, but it's a realistic situation. So I go from A, the cycle, we need to specify the cycle. So if I go from A to B, and then all the way back to A, AB is isothermal expansion. So from the discussion last week, we know that if we use ideal gas for the discussion, but it's okay. If you have an isothermal expansion, in general, you need to inject heat. Okay, so this is particularly clear when you talk about ideal gas. We can have very concrete prediction there. So you go from A to B. Isothermally, you need to absorb heat Q1. And where do you get this heat? This is provided by theta 1. Okay, and now you link these two together. Okay, and this is at theta 1. You see AB is on this line described by theta 1. And then if I go from C to D, this is on the dashed line. Again, is isotherm described by theta 2. If I go from C to D, I have compression. If I have compression, I will have to give up some heat. So that's why I have Q2. So Carnot cycle is a perfect cycle for me to realize this engine. Okay, so and if I have an engine based on the Carnot cycle, which means 2 isotherms and 2 adiabats, and this engine is called a Carnot engine. Okay, so Carnot engine is an engine based on Carnot cycle. Sounds very stupid, but this is the definition. Based on the Carnot cycle. Okay, so here you have AB. AB is okay. A, B, C, D. Isotherm. And BC and DA. Adiabat. Okay, so heat cannot enter. here. And now the question you ask is, what is the work done? The work done here is, if you have the PV diagram, if you get the coordinate of, now this is a PV diagram. If you get the coordinate of A, B, C, D, you can calculate this. You can calculate this very precisely. Okay, so how do you calculate? You integrate. You really integrate PdV. Okay, so now we also want to mention that we want to run this using the cyclic mode. So we go to A, and we go from A to B to D to A, and then again B, C, D, A, and then A, B, C, D, A, B, C, D, A, B, C, D. Okay, that is for two reasons. The one reason is this: once I go back to A. Now, the first law tells me U is a function of state. Once I go back to A, du is 0. And therefore, I can easily calculate for this particular cycle, per cycle, what happens to d bar Q. So the d bar Q has to be compensated by d bar W. Okay, that is to say, if I run the engine this way, there's some heat exchange involved. And this heat exchange involved will give me d bar Q. And where do they go? They have to go to work done. And this is the purpose of building an engine. I want to be able to extract work from here. And first law tells me I can. Okay. And the second thing is I want to always come back to the same point, so I don't need to build too many engines. I just need to build one, and then I can reuse it again and again and again and again and again. Okay. And the work done, now we know there's a work done. The work done can be obtained by integration. So I will just put this absolute sign here to be consistent with my note. And also this seems to be a universal convention, because now when we talk about engine, we draw this arrow this way, which means we want to look at the heat output. So there is the heat given by the system, by the thermodynamic system. So using our definition, there will be a minus sign, but I don't want to worry about the minus sign. So I would just use the arrow to tell you the direction of the energy transfer, and then I would just take the absolute value like this. Okay, so just be careful. A lot of book just assume you have you understand this arrow, right? And what we really mean is we just look at the absolute value of W, and then we look at the relationship between the absolute of Q1 and Q2 with W. Okay, so in this case, you always see this. The W is the difference between the heat which you originally have. You originally extract so much heat, and then you have to dump away some. Okay, and the remaining will be converted to work. And this is kind of intuitive here. Okay, and this is work per cycle. This is the energy you extract from theta 1 per cycle, and this is also per cycle. So everything is per cycle. Okay, so just be careful when you read this part of the note. Okay, so now we can finally come to this key question. This is the efficiency. The efficiency is defined as what you can get from the engine compared with what you pay for it. Okay, so this is what you pay, right? You give the engine so much, you pay so much heat energy, you want to get a lot of work done. So ideally you want this to be 100% efficiency, but I already told you this is impossible. Okay, so this is the, I will drop the absolute sign because now it's clear. This is the difference between the two heat energies, and this is Q1. Okay, and you see this is the efficiency formula. So if you don't have Q2, then you have 100% efficiency, but this is not allowed. You will always have an efficiency which is less than 1. Okay, so another important thing which will be useful for us is when we talk about a heat engine based on the Carnot cycle, this Carnot engine is always reversible. So this Carnot engine is always reversible because if you look at this diagram, you do not have any path which is not reversible. Okay, so if you have one segment which is not reversible, the entire engine is not reversible. Okay, and Carnot engine is an engine which is always reversible. Okay, which means you can operate this backward. And thermodynamics, the second law, allows you to have a Carnot engine which is operating backward. Right? And this is not always true. You be careful. Here, that's to say, I'm allowed to flip the direction of all the arrows, and that is allowed. Okay, and now I hope you understand, right? Here, I flip the arrow. From here to here, I flip the arrow. This is not allowed. This is people try to do it and discover that this is impossible, and this is the not K. Right? Not K. K is Kelvin. And here, for a Carnot cycle, once I build a heat engine which is allowed, and I use a Carnot cycle, I already explained to you that I can build it using the Carnot cycle, and I can flip all the arrow, and this is allowed. Okay, so Carnot engine is reversible, and then to be even more precise, Carnot engine is an engine which is operating, is reversible, and this is an engine which is operating between two reservoirs only. Two reservoirs only. This one will be useful because later we are going to generalize to an engine with many reservoirs. And how do we deal with this kind of complicated situation? We actually will come back to our Carnot engine and try to connect all these engines together in order to extract information. Okay, so this is a heat engine. We already talked about this. And now, before we leave, I want to present two situations. Okay, so there is two impossible engines. Okay, I think I can do it this way. Where is I think I can copy this. I can copy this. Okay, where is it? Okay, I want to tell you two engines that are not possible. So this is engine 1, this is engine 2. Then we will finish. Okay, the first one which is not possible, you already seen. If I take Q1 and convert everything to work, this is not allowed. Okay. And the other one which is not allowed, you haven't seen, but I'm going to draw you now. If you have an engine which extract heat from Q2 and dump it to Q1, but now I don't involve work, so Q1 and Q2 are the same, so I just use the same symbol. Okay, this is also not allowed. And this is also cool. Actually, you already kind of guessed this, right? You can, I told you I can have a heat transfer from hot body to cold body. And you might say, okay, I'm very smart. I'm going to build I told you from cold to hot is not allowed. Okay, so now you say I'm going to build an engine to carry out this operation, right? So this is essentially taking heat from the cold reservoir and dump it to the hot reservoir. So I will have a net effect of transferring heat energy from cold to hot. So heat flow comes from the cold body to hot body. I want to build an engine like this. Now, unfortunately, this is also not allowed because you don't really supply work. Okay, so this relates to two statement of second law. Okay, so I'm going to give you the statement, and then we are going to stop here. Okay, so I will have this one. Sorry, this is the one on the left is Kelvin's statement for the second law. Okay, so let me make it bigger for you. And the one on the right is the Clausius statement. Okay, and our task is to show that these are the two different statements for the second law. Okay, so this is really the Kelvin statement of the second law. And this is the Clausius theorem. And they are actually equivalent. So the task on Wednesday is to show that they are equivalent. And now you can now understand why I put this tilde here, because look at the statement. The statement basically is telling you that you cannot have an engine or process. The sole result is the complete conversion of heat into work. This is not allowed. Okay, and if you admire this again, it's basically about what I just said. The transfer of heat from the colder body to the hotter body is not allowed. And how do you make it true? You have to allow some work done. Okay, so if you allow the work done, if you draw an arrow like this, I will draw by erase later. If you draw it like this, this is allowed. Okay, so again, this has to do with spontaneous, right? So if I interrupt the process like this, this really means I'm running this as an engine, then this is okay. All right, otherwise this is just really like a heat transfer. This is just some intermediate body, and this is a hot body, hot body and a cold body, and then this is just a heat transfer from cold to hot. Okay, that's all for today, and I will stop here. I will stop the recording.